Donostia International Physics Centerreko txit lehendakari jauna, Osakidetzako sailburu Andrea, gurekin zaudeten irakasle eta bizitari ospetsuak, Mr. Ciechanover, Mr. Ernst, Mr. Langer, osasunaren, ikerkuntzaren eta berrikuntzaren komunitateko kide eta lagun guztiek, egunon eta ongi etorri. Thank you for your visit. Be welcome our home. Mil esker gurekin zientziagune honetan egoteagatik. Gracias a todas y a todos por estar con nosotros en este momento casi inicial del Congreso Passion for Knowledge, que conmemora la primera década del Donostia International Physics Center, del cual Kutxa es uno de los patronos. Creemos que va a ser un congreso muy importante para la comunidad científica, pero, y sobre todo, para los que no perteneciendo a ella, estamos muy interesados por el conocimiento y por la difusión de la ciencia. Cuando un acto, ciclo o congreso comienza, yo soy de los que piensan que es el momento de felicitar a los organizadores. No me cabe ninguna duda, vista la capacidad demostrada por el líder y el equipo que se han ocupado de poner en marcha este congreso, que ya tienen asegurado su éxito. Beraz, Pedro, zeuk eta zure taldekide guztiok, jaso itzazue gure onespena eta gure eskerrak egin duzuenagatik eta egin behar duzuenagatik ere. Y no es casualidad que este congreso comience por este encuentro con profesionales fundamentalmente del ámbito biosanitario. En mi opinión, la sociedad tiene una verdadera prioridad, una clara fe y confianza de que las ciencias relacionadas con la salud y la calidad de vida avancen hasta asegurar su máxima aplicación eficiente e igualitaria en condiciones para todas las personas de este mundo. La pasada semana nos reuníamos muy cerca de aquí, dispuestos a poner la primera piedra del edificio Biokutxa, una infraestructura que esperamos llegue a ser trascendental para el futuro de la investigación en Guipúzcoa y que contribuya al desarrollo y el bienestar venidero de los guipuzcoanos. Tampoco puedo dejar de citar a Onkologikoa, principal agente en la estrategia de Kutxa en el ámbito de la prevención y el tratamiento del cáncer. Y, por supuesto, otros proyectos que hemos impulsado en los últimos años. Biomed, fundamentalmente, y ahora Biodonostia, Cita Alzheimer y otros venideros. El futuro y el progreso de cualquier sociedad pasa necesariamente por su capacidad para innovar, por su potencial para investigar y por los recursos, tanto humanos como materiales, que pone a disposición de la investigación y del desarrollo tecnológico. Y en este ámbito, Kutxa tiene una clara vocación de apoyar la ciencia con mayúsculas. Los datos demuestran que somos una de las entidades líderes en lo financiero, cuestión muy importante en estos momentos. Y también creemos y queremos serlo en todos los campos de lo social, especialmente en el campo de la medicina regenerativa, que es, como todos vosotros sabéis, un área de desarrollo esencial en la biomedicina presente y futura. Agradezco la oportunidad que los organizadores del Congreso nos han dado para colaborar con ellos y ponemos en valor el avance que estos 10 años ha generado el Donostia International Physics Center. Esperamos que celebremos y celebren muchos como este para celebrar décadas sucesivas. Thank you for your attention, mil esker zuen arretagatik, eta opa dizuegu arrakasta handi bat gaur eta beti. Gracias y espero que disfruten con nosotros. Agur.
Good morning, ladies and gentlemen. Today is going to be a great day, a day for the memory. It's something that doesn't happen very often, to have the possibility to meet, to have the possibility of sharing 2 hours with such a level of scientific knowledge creators as Mr. Ciechanover, Chemical Nobel Prize 204, Richard Ernst, Chemical Nobel Prize 1991, and Mr. Langer, among 170 other recognitions, Prize Príncipe de Asturias 2004. Welcome to our country and to this celebration of knowledge that Pedro Miguel Echenique has offered to us. Thank you very much, Pedro, for this occasion. But this meeting is also a rare occasion because it's not frequent to have together almost 100 of researchers from our powerful, energetic and growing Basque biocluster, covering from the scientific to the clinic link of the knowledge value chain and representing industry, research centers, universities and hospitals. Thank you to all of you also to be here ready to learn and share. I was trying to figure out which is the level of intelligence per square meter here in this room this morning. And I don't know really, but it doesn't matter. I'm sure that this is going to be an issue that gives us the possibility to expect great results for this meeting this morning. And not only because of the potential of this intelligence, but also because of our strong motivation, our real passion to create and applicate knowledge. We are lucky to work in a domain where knowledge, science can be used very fast to save and improve lives, thanks to the commitment of all the actors and all the constituencies. In the Basque Country, we are not only committed, but ready to contribute. Government determination for invest still more. We have already invested for decades. Tell us that the time for harvest is coming. Promoting dialogue, interconnections and knowledge sharing will be critical to improve our capacity of advancing in that direction. This morning I was coming here with a vision in my mind. I saw that in 7 years from now on, doing the official presentation of a new treatment, pioneer in the world and ready to save millions of lives, in the board that was presenting this, somebody said that it was not possible if this meeting, celebrated on Monday, 17th September of 2010, in room Newton of Cucha Espacio de la Ciencia, this would have not been possible. And you are all here as actors and witnesses of this day. Thank you.
Bueno, egunon, eskerrik asko, Olgari, eskerrik asko, Carlos Ruiz, eman dituzuen hitzaldi bikaina edo hitzalditxo bikainagatik. Agradecer también a los asistentes, sobre todo viendo la clase médica por la puntualidad de los que ya han llegado aquí. En cualquier caso, cuando en Cucha nos sentimos como en casa, porque la exposición de Carlos me ha hecho recordar que el Passion for Knowledge empezó con la lección de Julio Linares en el DIPC, pero sobre todo con las conferencias Cucha, que fue una idea que él impulsó, en que calentamos motores con diversas conferencias para estar preparados para oír a los protagonistas de esta semana. Y la primera conferencia que yo tuve el honor de impartir, y veo aquí bastantes que estuvieron en esa conferencia, se titulaba La sublime utilidad de la ciencia inútil. Y allí yo empezaba recordando apropiadamente el discurso que a finales del siglo XIX impartió en la Sociedad Americana de Física Henry Rowell. En ese bellísimo discurso, él se pregunta, y además es especialmente conmovedor, porque las preguntas que él hace en abstracto y refiriéndose a su mujer y a su hija se referían también a él. Él muere año y medio después de este discurso, de diabetes. El remedio de la insulina creo que se encuentra 20 años después de este discurso. Y en ese discurso él se preguntaba por qué cuando el médico viene a vernos, lo único que me puede decir es que no puede hacer nada para aliviar el dolor y la muerte inmediata de mi hija y de mi mujer. Y él mismo, en el discurso, encuentra la respuesta a su pregunta. Dice, la razón es la ignorancia. No conocemos suficiente y no sabemos el remedio. Y por supuesto, él se pregunta luego, con gran visión, que el problema no solo es de la medicina, porque el cuerpo humano es un complejo mecanismo, tiene complejos mecanismos en los que intervienen para entenderlos la física, la química, la biología y otras ramas del saber. Y formula un deseo. Podremos aspirar, este deseo está formulado a principios del siglo XX, que al final del siglo XX este sufrimiento que yo tengo que soportar no lo tengan que soportar los que vengan, las nuevas generaciones. Y esto es exactamente lo que ha pasado en el siglo XX. El siglo XX es el siglo de muchas cosas, pero también es el siglo del triunfo de la ciencia y la tecnología en reducir la dependencia con la naturaleza y en posibilitar que nuestra vida sea más larga, más humana, en una palabra. Por supuesto que la mitad de la población mundial permanece desconectada de este avance. Este triunfo de la ciencia y la tecnología, en parte, se debe a la física, con dos pilares fundamentales, las teorías de la relatividad y, sobre todo, la física cuántica. Pero a un mecanismo, se debe a la pasión de los científicos por el conocimiento, teniendo libertad para formular las preguntas y la forma de contestarlas. Y se basa también en una responsabilidad social, de preocuparse por los problemas de la sociedad e intentar soluciones. Por eso, un instituto de física ha convocado esta reunión a cuya asistencia les agradezco. ¿Por qué? Porque los físicos no solo hemos aportado a la medicina y a la biología los instrumentos, o los químicos, porque aquí está Ernst, estos son de todo, pero son físicos, químicos, ingenieros, habilidades y conocimientos. Los físicos o los químicos no solo hemos aportado los instrumentos, habilidades y conocimiento, que también, pero también hemos aportado, transmitido la necesidad de buscar comportamientos físicos radicales o explicaciones físicas radicales del comportamiento celular. Y hoy la investigación del futuro, como han dicho estos eminentes científicos y otros, en medicina y biología no va a ser únicamente para investigadores biomédicos. Uno de los desafíos más importantes de la medicina será el integrar los avances en física, química, ciencia de materiales, ingeniería química, biología y nanotecnología. Esto es lo que nos aportará un conocimiento más profundo de las causas de la enfermedad. Y por eso hoy nos congratulamos de tener 3 ponentes de excepción. La biografía de ellos la conocen, la han visto estos días en los periódicos, están en la Internet. Cualquier persona medianamente informada o formada, no ya médico, sino culturalmente bien informada, sabe quién es Robert Langer, el inventor más prolífico de la historia de la medicina, un ingeniero al servicio de la salud humana. Sabe quién Ernst, que no solo es un gran químico o ingeniero, porque trabajó 5 años en una compañía como ingeniero, el que nos ha ayudado a ver, para entender mejor el cuerpo humano. o Ciechanover, que es médico biólogo, con su búsqueda de nuevos medicamentos. Y nosotros les hemos invitado por un convencimiento profundo. Así como no puede haber una buena universidad docente si no es buena universidad investigadora, creemos que un buen hospital también tiene que ser en el futuro un buen centro de investigación. Lo cual no quiere decir que la transición tenga que ser molestando a los que no son investigadores y que no pueda haber grandes médicos que no sean investigadores, como los hay. A mí muchos de ellos me han tratado bien, son investigadores, unos sí, otros no, pero yo soy uno de los grandes beneficiarios del Hospital de Donosti. Y no quiero entrar en detalles, pero aquí hay algunos de los que me han cuidado también. Nuestra idea, pues, es transmitirles que el futuro va a ser colaborar entre todos y que investigar es un imperativo ético con el futuro y con las nuevas generaciones. Y para eso, hoy traemos 3 ponentes que tienen talento, que han trabajado en libertad y constancia. Los 3 lo han dicho. Si se tiene una idea hay que seguirla, seguirla, seguirla. Sin desanimarse, siempre se logrará el resultado. Otro Nobel suele decir, lo difícil lo hacemos inmediatamente. Lo imposible requiere un poco más de tiempo. Y luego, este conocimiento no es un conocimiento solamente para el disfrute intelectual, que también, sino para poner la ciencia al servicio de la sociedad. Y no hay mejor ejemplo que la medicina. Por eso ahora vamos a recibirles con un aplauso y ellos hablarán durante 10 minutos y después en un coloquio absolutamente informal, con plena tranquilidad, en el idioma que quieran, pueden preguntarles. Yo he elegido hoy hablar en castellano porque mi castellano es mejor que el euskera. Pueden preguntar euskera, hay traducción o en inglés o en el idioma que quieran. Muchas gracias por haber venido, and thank you very much, sirs, for having accepted our invitation. Please. Well, primero, first, Professor Lange will speak, after Professor Ciechanover, and after Professor Ernst, and then we begin talking and discussing. Una vez que hablen, ustedes formulan las preguntas que quieran, los comentarios que quieran, sobre el tema que quieran, y seguro que encontrarán respuestas buenas y brillantes. Muchas gracias.
Thank you. It's a pleasure to be here. Okay. Do you want me to stand or?
Whatever.
Is this people? Can people hear me? Okay.
Yeah.
Thank you. So my background is, as was mentioned, is that of being an engineer. I'm actually a chemical engineer, but when I graduated from university in 1974, I actually did something very unusual for an engineer. I actually went to work in a hospital. And I worked with a man named Judah Folkman, who was a surgeon. And what I thought I'd do is tell you a little bit about what I did there, which began enabling me to apply engineering to different medical problems up to some of the things we're doing now today. I'll probably do this in 3 areas. Well, the first thing that when I began working with Dr. Folkman, he was very interested. He had a theory that if you could stop blood vessels from growing in the body, that might lead to new kinds of medications to treat cancer and other diseases. In fact, at the time when he proposed it, it was quite controversial. What I did for my postdoctoral project is he asked me, could I isolate something that could stop blood vessels that hadn't been done before? And he wanted to see if we could prove that. So I actually started by getting material in cartilage, which is in your nose or your knee, and trying to see if I could test different things in it. But the big problem, and this often occurs in medicine and biology, is how do you study something like how blood vessels grow? We didn't have any way to study it. So we decided to develop a bioassay. And the bioassay we used was the eye of a rabbit. So what we would do is we would put a tumor into the eye, and over about 2 months, it would cause blood vessels to grow from the very edge of the eye all the way to the tumor. So what we wanted to see is, could we now stop that from happening? Now, the challenge is that since that took 2 months, we had to have a way to give the medication right to the tumor very, very slowly and in a way that did not hurt the eye. So what we thought is maybe we could create a little plastic or polymer that could take any of the substances in cartilage and slowly deliver them. The problem, however, is most of the substances in cartilage were fairly big molecules, and there was no plastic could deliver them slowly. So actually what I had to do for my earliest invention was to figure out a plastic that could slowly deliver these substances. So it took me many years and hundreds of failures, but eventually worked out a way to do that. And because we were able to do that, we actually were able to do two things. One, find a substance that could stop blood vessels from growing, and two, create these little plastics that could deliver medications for very long times. Today, both those areas are moving forward. There are now, as you may know, many different substances that different companies have isolated that stop blood vessels from growing. Some of them are used now in new cancer treatments, like Avastin. Some are used to treat macular degeneration, which is a leading cause of blindness. Also the plastics that we developed, those kinds of systems are now being used to deliver different drugs in different treatments. Like there are peptides, for example, people want to use in prostate cancer, but you can't swallow them because they're big or put them in a patch because they're big. So people now inject them, but if you didn't put them in a little plastic like this, it'd be destroyed right away. So there are many little what we call microspheres that you can inject now to treat prostate cancer, endometriosis, schizophrenia, alcoholism. There hopefully will be one approved by the FDA in 2 weeks to treat diabetes. But so these are all now being quite active. Also, what this began to provide is the beginnings of medical nanotechnology. Because if you could make little microspheres like this to deliver molecules, we could now make them even smaller to inject them into the bloodstream, and sometimes have homing devices that might be able to take them right where you want, say a tumor. We haven't, nor have others, totally solved that problem yet. So that's an area of very, very active research in the world, is using nanotechnology for drug delivery and other areas of medicine. The second area I wanted to go over, I also learned at the hospital. Since I started working on materials, I became very curious, how did materials get into medicine in the first place? And I was very surprised. I would have thought great chemists were responsible for getting materials into medicine. But when I looked at this in the hospital, I found it was always medical doctors. But what the medical doctors always wanted to do, because they urgently wanted to solve the medical problem, is they almost always went to their house to find an object in their house that resembled the organ or tissue they were trying to fix. So if you look at this today, the artificial heart, the material in the artificial heart is a lady's girdle material. Breast implant, that material is actually a mattress stuffing. What's called a vascular graft, artificial blood vessel, that's closed because a surgeon wanted to sew it as well with it. So I started thinking, as a chemical engineer, you know, one of the things they teach you in chemical engineering is design, how to design different things. So just to go over, those materials that are used in medicine, actually they help solve some problems, but they also caused big problems. The artificial heart, what happens is somebody has an artificial heart, it doesn't work very well because blood hits the surface of that heart, forms a clot, and the clot goes to the patient's brain, they get a stroke and they die. The breast implants, people probably know, have had many problems. And you cannot make a small diameter vascular graft. So we said, well, can we apply chemistry and engineering principles to make new materials? And so we've made in our laboratory many different new materials. One is a set of materials that are now being used for treating brain cancer. These are materials that will slowly dissolve over different periods of time and locally deliver the drug right to the cancer. That's called the gliadel wafer. Another set of polymers which are still being studied are ones that can actually change their shape. You might be able to someday, and again, we're still working on this, use minimally invasive surgery. Make a little hole and put a string in through that hole. But when it changes temperature, it could change its shape and go into whatever type of device you might want, like a stent or a sheet to prevent adhesions or things like that. We're also trying, and again, we have a lot of work to do, to make new materials that might be useful for delivering DNA or siRNA to silence genes. The third area also involves materials, and also I've been working with another surgeon, Jay Vacanti, and this is the area that we started back in 1983 of what we call tissue engineering, which is a part of regenerative medicine. And what we've been trying to do is take plastics and engineer and synthesize them in the right way that you could then take different mammalian cells to put them on. And through that, what we've been trying to do is, could we, with the right materials, the right, what we call growth factors in the media, the right way to grow the cells, could we combine all these in such a way to make a new tissue or organ? In fact, today one might also be able to consider using stem cells as well as a patient's own cells, so that you'd have a very good cell source. Already, though, we are at the point where we can make new skin if somebody's burned or has a diabetic skin ulcer. But there are many, many others that are either in clinical trials or early-stage animal trials. Some examples that are in clinical trials are making new cartilage or bone, and we're also in animal trials for making new spinal cords for people who are paralyzed, and many other types of tissue. So a lot of work needs to be done, but the whole area of combining cell biology, these mammalian cells, with material science, these polymers, might someday offer a way to help solve many problems that now you cannot treat with drugs. In other words, if somebody needed a new liver, a new heart, we're also working on new pancreases, that someday this kind of field may be very helpful. So those are some of the things that we work on in MIT in collaboration with many different clinicians in the Boston area and around the world. Thank you.
Thank you very much, Bob.
Well, good morning. Let me start with a little bit of philosophy, continuing the ideas that were just raised by Bob. What Bob told you, in other words, as I understood it, that basically there are no disciplines. You know, we try to think of disciplines like physics and chemistry and biology and medicine and engineering, but if you think about historically, all these disciplines were created, well, we cannot pinpoint it exactly date-wise, but I assume at the 12th century when the first university was established in Bologna, for convenience of teaching, people divided the world into the world of particles that have no name, they called it physics. When molecules start to have a name and identity, they called it chemistry. When they dealt with biological processes, they called it biology. When they dealt with a human being, they called it medicine, and so on and so forth. But basically, nature has never heard of these disciplines. Nature has never heard of engineering, physics, chemistry, because everything is engulfed in this human being. And if you are following the development of medicine in the last 30 years, you see that there is a lot of engineering in it, lots of engineering. Actually, starting at the very beginning of the century, think of X-ray, of Konrad Röntgen, and then going to a much more sophisticated imaging technologies like MRI and CAT scan, and looking into material sciences, stenting, drug-eluting stents, and so on and so forth. So we are using heavy engineering in order to approach biological systems. And I think that that's what really occurring in front of our eyes, which is coalescence of all traditional disciplines that actually never existed because of tools that have been developed mostly along the last 2 or 3 decades that allow this, the creation of what we called interdisciplinary approach to biology and to biomedicine that actually is the natural approach, because again, this division is in many ways artificial. It was exemplified wonderfully by the three subjects that are the main focus of interest of Bob's lab. So let me now go back, because I'm coming from what's called biology or biomedicine. My background is very similar to yours. Actually, I'm a physician. I'm not only a physician, I'm a surgeon by training. And then I decided that I'm going to give up on daily practice, and I got interested more in basic mechanisms of disease, and I went to do a PhD with a wonderful biochemist, with Avram Hershko. And at that time we were interested in a biological process that nobody cared about, because it was still the time that the central dogma of biology, which is still now dominated the field, and the central dogma is, is the dogma of flow of genetic information from DNA into RNA and into proteins. Now we have new vocabulary. We are using the word, the flow of information from the genome to the transcriptome and then to the proteome. And nobody cared about the other side of the equation, how proteins are degraded. Proteins are generated, but somebody has to degrade them. And the reason that people were not interested, that from the very beginning and a priori they assumed that this is not an important process. When you look at the gastrointestinal tract, you take every beautiful protein, you take a wonderful piece of steak or a seafood or whatever, and within few minutes it's all gone, digested into amino acids, and we absorb the amino acids and then go and build again, according to the genetic information, our own beautiful protein. So people thought that this is an end non-specific garbaging type of a process. There were several hints that this is not the case. I will not go into all the milestones, but at the end of the day, along with my mentor and then continuing working on it by myself and in collaboration, when I was a postdoctoral fellow at MIT, we discovered a wonderful system that is a highly specific system that degrades only proteins that need to be degraded at a certain time. And just to give you one idea about what's going on with protein degradation and why it's such a sophisticated process. Proteins are very sensitive molecules. They are very large molecules, and they are under effect of all kinds of post-translational changes, like temperature. Think about temperature. Proteins don't like to be at high temperature. They certainly don't like to be at 37 degrees, which is deleterious to proteins. I mean, think about a piece of meat that you are leaving on the table, or a glass of milk that you are leaving on the table at room temperature, 25 centigrade for several hours. You come after several hours, it's gone, it's useless. And think about our body that have the same very proteins that we carry on or for decades and nothing happens. Well, we are not carrying the same proteins, because every day we are destroying the misfolded, the denatured protein, a process that occurred because of high temperature, because of oxidation, because of many other processes, and we replace them. So we need to replace, for quality control, about 6 to 8% daily of our proteins. So the process is highly specific, and if it's going wrong, there are many diseases that we call now quality control diseases. Many of the neurodegenerative diseases like Alzheimer and Parkinson, polyQ expansion disease like Huntington disease, are all attributed to malfunction of the quality control mechanism in the body. Even cystic fibrosis is attributed to this. So gradually, based on our discovery, people discovered that there is a whole huge process in the body that cleans, that keeps the body tidy, clean of the misfolded and denatured proteins. And aberrations in the process lead not only to neurodegeneration, but also to malignant transformation. And there are many diseases in which there are aberrations in protein degradation that lead to malignant transformation, to inflammatory disorders, and so on and so forth. And then the next step was drug development. So there is already one drug. Probably there are any hematologists in the audience? Hematologists? No hematologists. Well, there is already one successful drug in the market based on this discovery that, again, at the very beginning, people looked very weirdly at what we are doing, kind of searching for something that is type of a garbaging mechanism. There is a drug to multiple myeloma. Multiple myeloma is a type of a leukemia. It's an expansion of a B cell. This is the immune cell that generates immunoglobulin, and there is a very successful drug in the market already called Velcade that really changed in many ways the landscape of the disease. And again, once we are talking back on interdisciplinarity, you all know that the chemotherapeutic drugs are now delivered in a systemic way, and therefore they cause lots of damage, and we are looking for advances in engineering, let it be imaging, that we can deliver drugs just to the tumor via identifying the artery that supplies blood directly to the tumor, and many other nanotechnological advances that will be able not only to avoid the deleterious, the untoward side effects of the chemotherapy, but also build the high concentration of the drug in the tumor rather than distributing it in 99% of our body mass that doesn't need the drug, and actually the drug is causing side effects. So you see that each development is linked immediately to other development that should come from other fields, and therefore there is the need for this type of collaboration. Last word on the future of medicine and the buzzword that we are all talking about, which is personalized medicine. And we realize these days by sequencing the genomes of individual patients that have either breast cancer or prostate cancer or many other diseases, that our concept of the disease was all wrong. When we looked at breast cancer, we thought, well, this is one disease. When we looked even at malignant melanoma or many other diseases, we thought, well, this is one disease. But this disease was, the diagnosis of one disease was based, you know it all, on a very primitive approach to disease diagnosis. It's mostly the hands of the doctor, even the most sophisticated imaging techniques that don't have the capacity to go molecularly to analyze the disease. And we are using also a 200 or 300 years old device, which is called the light microscope, and the pathologists, which tell us, yes, this is the breast cancer grade 4 that invaded the basal membrane or didn't invade the basal membrane, and the nucleus looked corrugated, and so on and so forth. But you all know that molecularly this is all useless. So we are going now to molecular diagnosis, and the molecular diagnosis is rather complicated. It's complicated because it tells us that in each disease, like in cancer, there is not one mutation or two mutations, but there are hundreds of mutations. And we don't know which is the chicken and which is the egg, and the mutations are different from patient to patient. True, many of them belong to major pathways, like signal transduction pathways, but they are nevertheless different. So we are hoping, but this is a very complicated hope, and there will be the road to personalized medicine that will fit the patient repertoire, genetic repertoire, is very complicated. We hope to be able to tailor specific drug to specific set of mutations, but don't forget the information is not only embedded in the DNA. DNA itself undergoes post-translational modifications like methylation, silencing, opening, and so on and so forth. Then there is the translation, and then we have the proteins, and all the drugs, or many of the drugs, are directed towards the protein, and the proteins themselves are undergoing post-translational modifications like ubiquitination, acetylation, phosphorylation, amidation, and so on and so forth. And these are all labile changes. So, you know, when we speak of the genome, we think, yes, the DNA is stable. But the DNA is not stable, and the RNA is not stable, and the proteins are not stable. So the road is still there, where we do want to tailor specific drug to the specific repertoire of the patients, but the road is going to be very bumpy because it's much more complicated than we thought. Initially, we thought, for example, that cancer will be one mutation, maybe one mutation that follows the other, but then just recently in the Broad Institute, people started, and worldwide, people started to sequence genomes of patients. So 500 genomes of breast cancer patients or prostate cancer patients were sequenced, and the surprise was huge. 300-400 mutations per tumor, and many of them are different from one tumor to the other. So how do we go about it? It's going to be complicated, but we must traverse this road in order to solve the problem. So I think that the future road in medicine is going to take us via an unbelievable, exciting road that will involve both basic research in biomedicine, understanding the very basic mechanisms, but accompanied by very sophisticated imaging, delivery, and engineering devices that will combine all together to find the drugs of the future. So I think that this is the message of the future in biomedicine. Difficult, long, but possible and hopeful. Thank you very much.
Professor, is it open?
Okay, yeah. Buenos dias. It's indeed a great pleasure for me to be speaking in front of some of the very best medical doctors of the Basque Country. And, you know, my life has developed strongly related to medicine. My delivery initially was under medical assistance, and I'm sure that my disappearance will be medically assisted, because last year I was in a hospital and they did some brain imaging using MRI, and they found a stenosis in my brain. And my doctor afterwards told me I shouldn't worry too much. I will have a very easy death. I will not feel anything. So, and in between, I'm supporting medicine. I'm going weekly to a medical doctor and providing him some decent business. So I'm serving as a sample for them, as a way of income, and at the same time they are helping me. So this relation has developed very importantly. For example, a few months ago, again, I was in hospital, and what they found is a completely blocked artery in my left leg. And they had to put in a new artery, a bypass operation in the leg. And without MRI, I wouldn't be here today, or I would be here probably in a wheelchair. And now I just have pain in my feet, and I have to come with sandals instead of shoes. But that's the only disadvantage which is left from that surgery. Okay, I'm not a medical doctor, and I understand very little of medicine, and I'm just a victim of medicine. And, you know, originally I wanted to become a chemist. And I became a chemist, studied chemistry, and I mean, my professors at the university, that was ETH in Zurich, they didn't understand really what chemistry is all about, and I thought one has to investigate that in a little bit more details. And for that reason, I went into physical chemistry and tried to take advantage of physical methods, introducing them into chemistry to understand chemical processes. I went into lectures of pharmacology, but I mean, these professors, they really didn't understand anything whatsoever. They were just collecting facts and trying to relate the facts, but without any real understanding. And this situation was, of course, not very satisfactory to me. So during my PhD studies, I started to work on nuclear magnetic resonance. And nuclear magnetic resonance is a beautiful tool with which you can explore virtually everything. And nature, so to say, has put in spice into all materials, into molecules, into solids. Everything contains this spice, which you can use to ask questions, and you get an answer about the surroundings of this spice, and the spice are nothing else than nuclei. Nuclei with a magnetic moment. And so we used that at first for the exploration of chemical reactions, chemical molecules to determine their structure and so on. So magnetic resonance was originally developed for chemistry. At that time, that was in the beginning 60s, end of the 50s of last century, we didn't have such an instrument in Zurich, and we had to build it ourselves. And so I became an engineer building NMR spectrometers, and in the hope that I finally could use them to do some interesting experiments. But because my instruments never properly worked, I remained an engineer for my lifetime. And I'm still trying to make my instruments work. So I found engineering to be very important, and very interesting. And so to say, in the meantime, I have forgotten my chemistry. But soon other people made it work properly. And then, I mean, one of the major problems of magnetic resonance and the spice contained in all the nuclei in the molecules, they are very weak signal providers. The signals are very weak, and sensitivity is an enormous problem. So the first success we had was the development of Fourier transform spectroscopy, where we tried to address all the nuclei at once. I mean, before one was scanning through a spectrum line by line, took a lot of time. And then we devised a scheme where one could in parallel address all the nuclei at once. That led to Fourier transform spectroscopy, and it was a great success and made NMR much more practical than before. And then we were starting to become more interested in structures of molecules, and for that we developed two-dimensional, three-dimensional, and multi-dimensional NMR, where we record two-dimensional or three-dimensional spectra which give you relations between the different atoms and telling you something about the structure of molecule. So that was quite successful. That was in collaboration with Kurt Wüthrich, who finally also got the Nobel Prize for the same. That was an important development for molecular biology. So one could look then at protein structures, interaction of proteins, functioning of proteins. That was an important development, and NMR proved to be not only essential for chemistry but also for biology. And finally then the development went into medicine. I didn't have that idea to do imaging with magnetic resonance, and I never actually thought it would ever be possible. We had already problems with our very small sample tubes where we had our molecules in, and we never could conceive that one could put a human being into a magnet and look at his inside. But finally it turned out to be possible, and in the very first phase of magnetic resonance imaging I thought, yeah, I mean, it probably will never make it, but let us make a small contribution ourselves for the case that it will succeed. So we published a paper, and that paper became important. That was again Fourier imaging, using Fourier techniques for imaging, an alternative method to what Paul Lauterbur had suggested initially. He suggested a projection reconstruction technique. We introduced the Fourier technique, which proved to be superior, and which is the basis essentially of all the imaging techniques today. I mean, at that time, initially I was working in California for Bere and Associates in Palo Alto, because after my study I swear I will never go back to a university. I don't want to live in an ivory tower. I want to do something for mankind, something useful. And for that reason, I went to industry and worked for 5 years in industry. There we discovered this Fourier transform spectroscopy. And without my contacts to industry, I wouldn't have achieved what I did, and I wouldn't be here. So afterwards, I went back to Zurich again, where then the two-dimensional techniques were developed, and also as a small contribution to imaging, which I just mentioned before. And I patented it and gave the patent to Bere and Associates in Palo Alto for $200. And they made a fortune out of it. And at least I finally got a little prize from Stockholm, which made it worthwhile anyway. So in the moment, I'm enormously glad that what I started led to something useful, and that's what I always wanted to do. And that gives me some kind of a satisfaction that my work was appreciated and led to something useful. But you know, we in science contribute not only good things. For example, we also contributed to the worst sickness which mankind is plagued with, and that's a hurry sickness. Hurry sickness, which we all suffer today. We run and run and run and run, faster every day. And for no good reason. No good reason, only because the neighbor is running even faster than we. We also run. And in the evening, we are stressed. We try to go home and we see our children. We don't have time for them. So that's also a consequence of science. That's also a consequence of science and not a positive one. And I'm also contributed to it, speeding up NMR, making NMR much more faster and more useful. So it has both sides. It has both sides, and we have to live with these two sides and to try to accommodate them properly. Thank you for your attention.
Now we began the discussion and the questions. Si hay alguna pregunta, algún comentario, a ver quién es el primero que se anima. Si no, como conozco a varios de la audiencia, os voy a pedir directamente que hagáis la pregunta. A ver, José Félix.
Voy a preguntar en español, aunque después las preguntas siguientes las hago en inglés. I will ask the questions in Spanish. Como neurólogo, probablemente una de las preocupaciones más importantes en este momento es las enfermedades neurológicas de la vejez. Yo creo que la enfermedad de Parkinson y sobre todo la enfermedad de Alzheimer es una preocupación muy importante para todos los que estamos ya en una edad próxima a poder sufrirla. Y por lo tanto es bueno que nos planteemos preguntas de qué podemos hacer para tratar de prevenirla fundamentalmente y después tratarla, diagnosticarla precozmente y tratarla. Yo creo que tenemos en la cabeza los médicos una idea que es falsa y que antes ya se ha planteado en parte en la exposición que se ha hecho. Parece que las enfermedades tenían que ser o genéticas o ambientales y que las enfermedades genéticas se podían detectar a través de modificaciones del DNA. Hoy ya estamos comprendiendo que el mecanismo genético no es solo el DNA, sino que es toda la transformación del DNA hasta una proteína que luego funciona y que probablemente en esa transformación influyen muchos aspectos ambientales de cómo se vive, ¿no? Y en la enfermedad de Parkinson, por ejemplo, esto se entiende que es el proceso final común de una serie de alteraciones a veces genéticas y otras veces por ahora no comprendidas desde el punto de vista genético. Hoy sabemos que modificaciones de proteínas como la alfa-sinucleína, como la parquina, como la dardarina, modificaciones genéticas pueden llegar a transformar finalmente en una enfermedad que es muy parecida en todas ellas. Pero hay gente que no tiene ninguna alteración genética y que termina siendo esta enfermedad. Entonces yo quería preguntar sobre todo en este intercambio de conocimientos cómo gente de otras áreas científicas, de física, química, podían ayudar a investigarnos procedimientos diagnósticos y procedimientos de comprensión de cómo estas proteínas que están alteradas inicialmente o transformadas, por ejemplo, hoy día la dardarina, el gen que codifica la dardarina, no sabemos cómo produce la enfermedad de Parkinson. Cómo esto nos podrían ayudar a comprender este mecanismo de producción de la enfermedad. Los estudios que hay hasta este momento con animales de experimentación, tenemos animales de experimentación producidas ya por mutaciones de este gen, no está claro en qué forma se transforma en enfermedad, ¿no? Entonces dices, ¿cómo nos pueden ayudar a comprender que proteínas alteradas pueden llegar a producir estos mecanismos de neurodegeneración? No sé si la pregunta es muy clara o no.
Did you get the question from the translator? If not, he will speak in English and make the question again.
Do you want?
Did you understand the question? Okay, perfect. So who, Bob, you want to answer? Aaron.
Well, this is a very complicated question, and no doubt you are right. No doubt you are right that neurodegenerative diseases, mostly Alzheimer and Parkinson, but also less common diseases like amyotrophic lateral sclerosis, Lou Gehrig disease, and Huntington. Not only Huntington, all the polyQ expansion diseases are really a main threat. And actually the prediction is, by looking into brain pathology, into tauopathies and other pathologies, if we are going to extend our lifespan to about 120, it's predicted that the prevalence of Alzheimer's is going to reach almost 100% if we are not going to do anything. Because we are starting to see, at the age of 90, 95, we are starting to see these pathologies already in almost 100% of the brains. It's just the reserve. And you know it, that for Parkinson, we need to lose about 80% of our dopaminergic neurons in the substantia nigra in order to see the first symptoms. So we have a huge reserve. Now, to your question very briefly, the answer is that we don't know what we can do about it, because what we can do about it depends on understanding the basic pathogenetic mechanisms. And I think that there are two approaches to it. There is what I call the bottom-top approach and a top-bottom approach. The bottom-top approach is just hard work. Taking, by the way, the genetic variants, like you mentioned, Parkin mutations and some other mutations, or SOD mutations in amyotrophic lateral sclerosis, that is only a small percentage. It's only 1 or 2% of all cases. Are cases in study. I mean, we are using it because based on these genetic mutations, we can generate mouse models, study the mouse models, and then go back to human beings. But unfortunately, most of those diseases are sporadic, they are not even familial, and they are probably very different from the genetic cases, though there is a lot to learn from the genetic cases. So understanding the genetic cases is important, but I'm not sure it's going to solve all the spectrum of these diseases. Now let's just go to the two approaches. The bottom-top approach calls for individuals, different laboratories, just to probe out the mechanism and to find what's going on with Alzheimer's. Is it the gamma secretase that cleaves incorrectly the APP or whatever? I don't want to go into all the mechanisms. The top-bottom approach, which is as legitimate, is an approach that is a kind of a fishing expedition approach. This approach says, we don't understand the mechanism, but let's go and sequence the genome. Let's go and develop a very sophisticated proteomic technologies and search in body fluids. Let's search biomarkers in the blood, in the urine, in the cerebrospinal fluid, everywhere, in tissue biopsies, everywhere. And those patients that are susceptible to the disease, we are going to discover the biomarkers. Now, the biomarker is only the beginning, because the biomarkers tells you where the biomarkers is derived from. Then you can go to the process that generated the biomarker. Hopefully the biomarker will be causative, not only kind of a hitchhiker, and then you'll be able to find the mechanism. So you'll say, I don't know anything, I'm just using very sophisticated technologies, genome sequencing, proteomic analysis, and go and find some marker that tell me, yes, this patient is susceptible to this disease or already has the disease, and then pull back kind of a reverse genetic approach and go after the mechanism. So I think that we are using both techniques. Different people are using both techniques in order to approach this disease. But certainly, I'm not here to prophesize, but the brain diseases are probably one of the greatest challenges, along with other challenges of this coming century, because as lifespan will expand, and it is expanding still linearly, in about 1 month per year. That's about it, I think. And it's still linear. I think that we are going to face a major economic problem, not only human and social problem, but a major burden on world economy in developed countries of these patients that are going to rely on assistance and help, and we need to approach these diseases. So this is not an answer to you. It's just highlighting the problem from a different angle.
You see, magnetic resonance is a beautiful tool which you could use for exploring, for example, Alzheimer's. You can do magnetic resonance imaging in the brain, and you can find where the brain is really diseased and where something happened. But you can also analyze it in much more detail in vitro, studying the interaction of proteins, the the clogging of proteins, which is so important in the development of Alzheimer today, when it's using solid-state NMR for that. These are all these beautiful detailed studies to increase your knowledge. But after all, you are not here for just exploring what happens, but you have to help the people. And to have helped the people, that doesn't mean to necessarily cure them, but you have to try to become used to the aging process. The aging process is inevitable, and you have to treat these people who suffer from their aging and to give them comfort and so on, and to treat them as human beings. And I think that's much more important than just studying their brain and saying, yeah, that's what is wrong with you. But I don't understand it completely, but I know a specialist who knows it even better and sends a patient to that particular specialist, and he sends it to somewhere else. That's not the way to do medicine. But medicine really means to help the individuals, take them serious, their pains, their concerns, and to prepare them for a life of finite lifetime. Life will end sooner or later, and just to prolong life forever is first of all impossible, and secondly it wouldn't make sense.
I think they cover it perfectly. That's okay.
Here. Que cada año que pasa lo vemos más claro. Every year it passes, when we grow older, we agree with you more and more. Next question, please.
Hola, gracias. Soy Javier Garjón, farmacéutico del Servicio Navarro Salud. Hasta ahora, cuando queremos trasladar un nuevo medicamento o una nueva tecnología a la clínica, el gold estándar de investigación es el ensayo clínico aleatorizado, que tiene un enfoque poblacional, saber si un fármaco funciona en una población. Pero aquí estamos hablando de medicina personalizada. ¿Esto va a cambiar el paradigma de investigación cuando queramos saber si un nuevo medicamento o tecnología funciona realmente en la clínica, en los pacientes?
Okay, Bob, this is too complicated for you. You want Aaron to answer that as well?
I'll try. Bob will take it.
I think that is it. Boy, these questions are very, very hard and very difficult. Well, I think personalized medicine is going to happen. I mean, to an extent, we start to see that already in certain drugs. I think some of the things that Aaron said previously will probably help. I mean, I think as you do genomic profiling, and things like that, I think that may enable you to see someday see populations of patients, where you could do much more specific clinical trials. So I do think as we go into the future, some of the things that he mentioned that are now going on will enable that type of thing to happen. It's happening in a few cases, and I think it will happen more and more as we get a better understanding of differences in patient populations. I think this died.
Do you want to comment, Aaron or Richard? Would you like to comment, Richard?
Sorry, I have to say I don't believe in personalized medicine. I mean, just think about an African country, and if you develop medicine which cannot be used in the poorest countries of the world, it's useless. And it will just lead to a split society, even more split than it is at this moment, between rich and poor within the country, between the rich and poor countries, and I don't think that this is a positive development.
Aaron, you believe?
I don't think that it's a matter of believing or not. Believing belongs to being religious. I think that personalized medicine is just a word that reflects development in science. If you have a woman with a breast cancer and she has a mutated EGF receptor, you want to treat her with Herceptin. If the EGF receptor is normal, you don't treat her with Herceptin because Herceptin will not help her. It's just a matter of the disease mechanism. You know, we can call it whatever name we want. We just fit the treatment, and as Bob mentioned, we are already there, but we are there in a very limited manner. We can call it personalized. It's a nice name. People don't understand what it is. They think that according to the name and their ID card number, we are going to send them a bag with a drug. This is not the idea. The idea is just to fit it more into the development and not generalizing the disease, putting the pathological entity under one umbrella, rather putting it into the right molecular context. That's all what it is. And we are doing it for prostate cancer, for, you know, testosterone sensitive or testosterone insensitive, and we are doing it for tamoxifen, for estrogen receptor sensitive or insensitive breast cancer, and we are already in there. All what we are doing in molecular medicine, we are trying to expand it. And by having the whole genome in front of our eyes, as I said, with word of caution, this is not going to be the whole story, because the story, we are going to, and with the development of more and more drugs, we are going to fit drugs into their targets more precisely. That's all what it is. I think that the division is very artificial. It's just reflecting the development and accumulation of knowledge, and unfortunately our naivete at looking at disease in an oversimplistic way beforehand, and as we unravel the real picture, it turns out to be more complicated. So I don't think that it's a matter of believing, it's just we are moving on with it.
Buenos días, Julio Arrizabalaga, de Enfermedades Infecciosas. Yo quería preguntarles en dos aspectos. Primero, si creen que con las nuevas tecnologías podríamos llegar a zonas que en este momento son auténticos reservorios, por ejemplo el VIH, lo podemos eliminar de determinadas zonas, pero está en determinados reservorios. ¿Pueden las tecnologías nuevas ayudarnos a poder eliminar estos reservorios? Y en segundo lugar, cada vez más los pacientes, según nos vamos haciendo, bueno, las personas, según nos vamos haciendo mayores, pues tenemos más posibilidades de llevar biomateriales, ¿no? Léanse, pues, prótesis articulares, tanto en cadera como en rodilla, podemos llevar marcapasos, podemos llevar desfibriladores. ¿Ven posibilidades de que uno de los problemas que tienen es la infección de estos dispositivos? Que podamos esterilizarlos sin tener que retirarlos en algún momento, por lo devastador que suele ser el cambio de prótesis de caderas o de rodillas. Estas serían las dos preguntas. Gracias.
I'll start with this. Well, I think they're two very different questions, both good questions. On the first one, and again, Aaron and others, you maybe want to add to this, but I mean, I think people are working on, not successfully yet, but vaccines for HIV. So to the extent that people are successful at that someday, and there's a tremendous amount of research on it, you know, I'd like to think that that would reach these pockets that you're talking about. And people are working on other medications as well. I think the second area, I believe will happen. I mean, we've already, in fact, there are companies now based on this work creating new materials that are make it very difficult to get infections. I mean, there's ways of treating surfaces, which now I know at least one company in the Boston area has. In fact, one of my students, Chris Luce, is doing this work where they've actually created materials that can, for quite long times, resist colonization and infection. And, you know, they're still in animal trials, but I think approaches like that, by treating the chemical surfaces either chemically or by adding, say, an antimicrobial protein or things like that, or peptide or things like that, I think those things will come to pass. So I think the long-term issues of infection will someday be eliminated.
Hello. Thank you very much for your presentations. And I'd like to ask you 3 questions. And the first 2 questions for Professor Langer. And before you mentioned something about a device for diabetes being approved by the FDA in a couple of weeks. Could you please give us any further information about it? And my second question is also related to the diabetes stuff. And I could read something about the MIT developing a continuous glucose monitoring device based on nanotechnology. Could you give us any briefing about it? And the third question for all of you, you all are very much devoted to these plastic devices and all that. I'd like to have your opinion about viruses as carriers of drugs and DNA and all that.
So I guess I should start. So the first question it was about the diabetes. Well, there are molecules now that have been developed, glucagon-like peptides, but right now they have to be taken many times a day because of their short lifetimes. But what's been done now, I mentioned how we did work in the 70s on creating new plastics like microspheres that could deliver drugs for a long time. So the specific example that I mentioned, which has now completed phase 3 trials, is something called Biosanitary, which would be a once-a-week injection of a glucagon-like peptide, which I think there's an FDA date in mid-October for deciding on its approval. But already in February, they said the human trials were fine. They just were worried about the manufacturing issue. So I think that's more minor. So that's the first one, which would be a once-a-week injection. It would be actually for type 2 diabetes in this particular case. The second question you asked? Yes, so they're using nanotechnology. There's actually a couple of approaches that have been developed at MIT, actually both we've been involved in. One is a little microchip that you can put underneath the skin that has these little nanowells in it and can last for very long times in the body. And the other is a way of non-invasively porating the skin, where glucose can diffuse from interstitial fluid to a monitor so that you could measure it, but you'll not break the skin. And your last question was, and again, others can add to that, your last question was, what do we think of viruses? Well, again, this has been an area of continual research where people started with retroviral vectors, and they've had some toxicity issues. Adenoviral vectors, they've had some toxicity issues. Now I think a lot of people are looking at AAV vectors. They seem to be better. Our own prejudice, because we like polymers, is we're trying to work on polymers that could someday be as good as a virus. And we've had some success in vitro and in animals, but we're not on human patients yet.
Just to the last question, I don't think that the idea is the viruses. The idea is to fit the envelope into the specific target cell, because you really want to send it as a missile. And I think that there is one example. Viruses can be very good trophic viruses that have trophicity to specific tissues are a good idea. But we have, for example, one drug which is called Doxil. It's doxorubicin that is put into a liposome, and the liposome has very specific affinity to specific tissue, and it's avoiding, because of the phospholipid composition, it avoids the heart, because doxorubicin has a deleterious effects on the heart. It led to myopathies and so on and so forth. So this is one example. So maybe trophic viruses, just the envelopes of trophic viruses, synthetically made, can certainly be used, I mean.
Más, pues.
Gabriel Zubillaga, Medicina Interna. Recientemente, en el New England Journal y en JAMA han salido unas relativas críticas, quizá, a algunas investigaciones, y en el sentido de que investigaciones sobre el genotipo de los enfermos o personas que tienen colesteroles elevados, con el Single Nucleotide Polimorfismos, SNPs, han demostrado en Estados Unidos que muchas personas que se han realizado esos test tienen alteraciones en esos SNPs y les han seguido durante 10 o 15 años a muchos de ellos y han visto que al cabo de los 15 años la mortalidad de esas personas dependía no tanto de esa genética alterada, sino más bien de los hábitos de vida, es decir, del consumo del tabaco, de la hipertensión, del colesterol, de la diabetes y los estilos de vida y del ejercicio. Entonces, ese artículo, de alguna forma, decía que solamente la genética ahí contribuía quizá a menos de un 5% de la mortalidad de esas enfermedades cardiovasculares en esas personas, seguidos prospectivamente durante 10 años. Había también luego bastante crítica en el New England últimamente de esas tiendas o comercios que pueden comercializar rápidamente microchips y aspectos que la gente puede realizarse a nivel ambulatorio, a nivel casi de anuncios de televisión y que de alguna forma no iría demasiado con los avances científicos, pero tendría un coste muy alto para las personas y no llevaría eso en sí al diagnóstico de enfermedades reales, ¿no? Y también el British Medical Journal había criticado últimamente que los médicos estamos exagerando a veces algunos diagnósticos o búsqueda de enfermedades y estamos llamando ahora prehipertensión, prediabetes, preosteoporosis, es decir, nuevamente quizá anticipándonos quizá a enfermedades que no existen o por la presión comercial de algunos laboratorios quizá.
Well, we cannot resist, the commercial companies are doing, they're selling chips, they want to genotype you. If people want to buy it and believe in it, I mean, it's their problem. If they have the dollars for it, it's okay. But let's go to the real fact. You're right. I mean, environment has a huge effect on our life, and from time to time, genetics is there in the background. So you have to have high cholesterol, and you can have it genetically without even being exposed to dietary cholesterol. You can eliminate eggs, you can eliminate whatever you want, and nevertheless, the beautiful mechanism described by Brown and Goldstein will produce huge amount of cholesterol. So, but it's true, environment, your behavior, weight, body weight, BMI is probably one of the major factors that correlates directly, and you are in full control of your BMI. You can just reduce the caloric intake and in many ways and reduce your weight and extend your life. Cholesterol, I think, actually, if you think about it, it's one of the diseases, so-called hypercholesterolemia, that really found a wonderful solution in the form of statins. So much so that I just read yesterday in one of the popular science journals that came out in Hebrew that some British researchers had the idea of adding Lipitor, just one tablet of Lipitor, or even half a tablet of Lipitor, into every McDonald's hamburger, and this will counteract immediately all the effect of the cholesterol that is coming with the hamburger. It turns out that cholesterol-reducing agents are fantastic drugs. The side effects are minimal. Less than 1 to 1,000 patients are suffering from some myalgia, some transient increase in liver enzymes, and so on and so forth, and they really made magic. I mean, the people that are using them, and we still don't know even the final results, because there are many studies, huge studies going on now on prevention by cholesterol-reducing agents, neurodegenerative diseases, like patients that have APO4E, this allele of the apolipoprotein that was linked to high prevalence, high incidence of Alzheimer's disease. So, yes, you're absolutely right. On one hand, there are these commercial companies that tell you, yes, it's all in your genes, and if you want to buy a chip or you want to sequence your genome, you can do it. I don't believe that it's going to be of any help. And then you're absolutely right. It's the style of life that really has an important impact on our quality of life and our, whether we are going to live healthy life or life that will be bumped all along the way with degenerative diseases. And all these diseases are basically degenerative diseases. Atherosclerosis is a degenerative disease of the intima, of the arteries, let it be the brain arteries, the coronary arteries, the renal arteries, whatever arteries. Parkinson is a degenerative disease of the substantia nigra. Diabetes is a degenerative disease of the islets, exhausting the islets of Langerhans in the pancreas from making insulin, and you have to really lower the pressure and reduce insulin resistance. So these are all degenerative diseases. And by reducing the pressure, either of cholesterol or of carbohydrates or whatever, we are certainly doing good to ourselves. Absolutely. And that's all in our hands.
Perfect answer.
You approve.
More than approve.
Hola. Mi pregunta va a ser bastante más amplia. Se va a tratar sobre los métodos que están ustedes siguiendo sobre investigación. Hi, Mr. Ciechanover. Y no sé si hemos superado ya la fase de especialización, viendo que aquí pues el señor Landon es ingeniero, físico, aquí es cirujano. Es decir, los nuevos campos de investigación han dejado ya atrás esa especialización, el científico que siempre solo sabía de algo, y se están abriendo a nuevos equipos multidisciplinares. ¿En qué manera investigan ustedes? ¿Cuáles son las nuevas formas de investigación? Y si estamos yendo hacia una investigación o casi a un hombre del Renacimiento, donde ahora mismo pues tienen que saber de todo: polímeros, metamateriales, ingeniería, química. ¿Hacia dónde van las nuevas formas de investigación? Y si hemos dejado ya la especialización, el científico especialista en su campo. Pues esa era mi pregunta.
Well, I think Aaron talked about this beautifully before. I think what's happened is, this is just my interpretation, is that for many, many years there's been enormous specialization. And I think now we're starting to see more interdisciplinary research that gives you more opportunities. I don't think that I think there's still plenty of what I'll call very disciplinary research, but I think we're starting to see more situations to solve medical problems that are very broad, where you do want to put lots of people with different backgrounds together. But I still think that's probably right now still a minority. Just to give you an example, at MIT, they still have exactly what he said. There are 20 different departments, all specialized in different areas like chemistry, physics, and so forth. But what they've started to do is to create institutes. So, for example, we're going to be moving into a new institute, hopefully to better address cancer research and other medical areas, in December. And half that institute will be engineers and half will be biologists. So I think the hope is that by putting people with different backgrounds together, you'll come up with new ways of thinking. And maybe we'll get back to where we were in the 12th century, which had some positive effects. But I think that we haven't, I still think that that's the minority of situations where people are put in, these interdisciplinary situations. Our lab, for example, also, one of my goals has been not only to try to invent some of these things in engineering, but to bring them all the way to, be used in humans. And to do that, you can't just have engineers. We have clinicians, we have biologists, we have, all kinds of different people. So I think it depends on the situation. But I'd still say, when I started doing this in the 70s and early 80s, we were probably the only ones, at least at MIT, that were doing something like that.
Yeah, I think interdisciplinary work is very important, and working together in teams is very essential. And so a team consisting of specialists is essential. But if you don't have a sufficiently broad knowledge which overlaps with your neighbor specialists, you cannot interact properly. And you need to have a broad knowledge in order to be able to understand what your neighbor specialist is doing. And only then you can properly collaborate. So broad knowledge and specialization both belong together. And I'm using for that normally the so-called T model, a T which has a stem which goes deep down into the foundations. That's your specialization. You have to know everything about very little. And at the same time, you have to have broad knowledge. That's the upper branch of the T, which is also important to relate to other fields. And only when you combine the stem and the branch together, then you are capable of having a fruitful interaction in a team.
Yeah, it's you know, there are two sides to this question, and I want to start with Richard's previous statement about that at the end of the day, there is a human being in front of the physician. And I think that the specialization, especially in medicine, raised lots of complaints on sides of the patients, that there is not only a cardiologist, but there is an ultrasound expert and a stent expert and valve expert and electrophysiology expert and insufficiency and heart insufficiency expert and so on and so forth. And patients are losing their ways. And they don't know where to go and what to do, and the expert can consult them only on one tiny small corner. So what to do about it is another, it's not only a professional problem, but it's also a social and a moral problem. And I think that Richard related to you know, we have a patient in front of us, a human being with feelings, with emotions, with family, with history, and, you know, how to deal with him as a whole, while he has a very specific problem that really needs an expert advice. So maybe, you know, people think about some coordinator of teams that will direct the patient, and then the patient will come back. But again, as Richard noted in his second comment, you need people that are experts, but people that understand several languages, that command several languages, that will be able to explain to the patient not only the very specific problem, but what the reflections of the problem on his lifestyle, on the quality of life, on the family, and so on and so forth, and also on his mental state. It's a very complicated, because medicine is an awfully complicated profession. So the side of the patient is one side of the problem. The other side is obviously research. And it's very difficult to solve, because on one hand, knowledge deepens daily and daily in every specific field, and you have to learn more and more on very little, as if to use the words of Richard Ernst. And on the other hand, we have to interact. What's very interesting here, what will be for researchers, the change in the culture of research. No doubt that we are going to work in teams. And though we see it coming drop by drop, I think that at the end of the day, in 10 years, 20 years, whatever, I don't want to prophesize, it's going to be an avalanche, and at the end of the day, it may be a new culture that we are working together. Universities will have to change their thinking, how to promote people, what is the contribution of each individual to the team. But no doubt that if you are developing a drug and you need to deliver it, you need to talk to the engineer, you need to talk to the nanotechnology expert. I don't think that there will be a Renaissance person. I think that, I don't know what's the limit, the capacity of the brain, but I think that it will be impossible for somebody to grasp the knowledge of everything. People will have, as Richard said, have a little bit of knowledge of their colleagues, so they will be able to talk the language, the basic language, and to understand how to communicate. But at the end of the day, there will be experts that will talk to one another and will work in teams, and I think that this will change the structure of universities. It will change the structure of the way we think of people, promote people, and so on, but that's all technicalities. What's really important is making the progress. How we do it will be just the needs, and it evolves by itself, because if people will need that they need to collaborate, they will collaborate. If they'll find out that in order to build an institute for cancer research, they need to have engineers, electric engineers, computational engineers, bioinformaticists, mathematicians, biologists, and physicians working together, they'll find a way to put them together. This is all technicality. I think that the needs will dictate the way that we are working.
Hola, soy Gurutz Linazasoro, neurólogo, y a mí me gustaría pedirles que hicieran un pequeño ejercicio de mirar hacia el futuro y preguntarles cuál es su visión las diferentes áreas de especialización que tiene cada uno en el futuro. Por ejemplo, si algún día será posible restaurar y regenerar áreas concretas del cerebro en base a ingeniería tisular, cuál pueden ser las futuras aplicaciones de la resonancia, cuánto puede dar de sí la resonancia magnética y cómo será el abordaje de los pacientes en el futuro, en la medicina del futuro. Esta sería un poco una pregunta general para los tres.
So could you someday regenerate the brain, parts of the brain? Well, I guess, see, my feeling is if you go far enough into the future, I think you'll be able to do most anything. The question is how far into the future. I don't think we're going to be able to do that quickly in the next 10 or 20 years. Some point, I think, as we continue understanding things, developing new technologies, I expect we will be able to do things like that. I just could not predict, what the time frame would be. On the resonance, I think we have much better people to answer that than me. So I'll turn that over.
Yeah, I think a lot of progress will happen in the future in understanding what is going on the molecular basis, on a more biomedical basis. We will learn a lot. But I think the crucial question finally is how can we implement that in medical practice. And I think there are limitations there. And I see a certain divergence between our basic knowledge and the application in a hospital, for example, or in a developing country or something like that. So I think we have to be selective and have to select those procedures which are practically implementable. And not all of them are of this type. So our knowledge will be much wider than what we finally can apply in practical applications.
Well, the problem is, again, very complicated. Take, for example, Parkinson's disease. People implanted cells, substantia nigra, already differentiated cells, into the substantia nigra, and there was improvement, but then there was a deterioration again. And when they went to do post-mortem, they found that the implanted cells got the disease from the neighboring cells. So there are lots of environmental. So it's not just, you generate stem cells, pluripotent stem cells, you differentiate them, and then you go and even put them in the right tissue. That's not sufficient. They need to acquire permanent type of healthy behavior. So it's going to be very complex. But on a philosophical point of view, I think that maybe this is the beauty of life. I always compare it to the Tower of Babylon. There is an old biblical story about people that wanted to understand the secret of God. So they decided, let's build a tower. And they called it the Tower of Babylon. It's kind of a spiral, and they wanted to climb up to the haven, and they hoped that they will get to God, and then they will discover. And then God didn't like it, obviously. So he somehow mingled them, he confused them, and the whole idea collapsed. If you think about modern history of medicine, think about it. At the beginning of the century, and I'm not talking about thousands of years, I'm talking just 110 years. At the beginning of the century, of the 20th century, people were living average of about 50 years, 45 to 50 years. We almost doubled it. They died mostly of infectious diseases. There was no antibiotics. Penicillin came to our world in the late 20s, early 30s. Ernst, Fleming, Alexander Fleming, and so on, and then Waxman, and so on, which was a major revolution. And we didn't know anything about cancer. Very few people died of cancer because we didn't live long enough to get cancer. Alzheimer was a very rare disease because, obviously, we didn't live long enough. And all of a sudden, by elongating our life, new diseases came to the world. Cancer became a major problem. Alzheimer became a major problem. We don't know what's waiting for us behind the corner. I mean, is there an end to... It's always a problem in medicine. Are we going... That's maybe part of the topic of my afternoon talk. Are we going to cure all diseases? Are we going to live in a disease-free world in 100 years and 200 years? I suspect that not. I really suspect that not, at least learning from history. It's going to be awfully complicated. We don't know what's going on behind. I mean, and it's very interesting whether we are believers that God put bumps on our road every 40 years. Initially, it was the infectious diseases. We still didn't defeat infectious diseases, by the way. We think we defeated them. They will come from the window now and from the back corner, from the other corners of the room. And all of a sudden, we discovered major other diseases. So it's going to be very, very complicated.
I'm Maria Jose Tames, hospital pharmacist working in oncology. And as a professional working in oncology, I'm really interested in this new delivery system for cytotoxic drugs. Looking at the old drugs we all know from in oncology, what are when you decide to create this old drug coming into a new delivery system, what are the factors you look at to choose the drug? In one word, why did you choose, for instance, the carmustine and not, for instance, 5-FU? It's a much wider use drug, is a very efficient. Why don't you choose, for instance, cisplatin, a very effective drug, and you choose, for instance, doxorubicin or other drugs? What are the main factors you look at for that, to try to start to work on this drug, to choose for it a new delivery system? And if you can advance or put forward an idea of what new drug in oncology we will see in the near future coming in a new delivery system.
Thank you. Well, first I think I should make a distinction between maybe what we do in academics and then what actually ends up happening as the progress is to move it to the clinic. So probably professors like myself, I mean, we might invent the delivery system, but I think what often happens whenever we do things like that, if it's a very, very new approach that's ever existed before, what happens, at least that what we find, is there's a lot of resistance in the medical community and even possibly the Federal Drug Administration to even approving it. So you asked, I think, it's specifically about why carmustine, and just for reference for people that don't know. So one of the things that we were involved in, as I mentioned, was creating these little wafers that would deliver drug directly to a target, and that's now used in brain cancer. So the clinicians we worked with, they chose carmustine for the simple reason that was already used to treat glioblastoma. And so the barrier to changing the resistance of the regulatory authorities and other clinicians, they thought would be less. So that's why they picked it. But also they thought, and I think that they were right, was that opens the door. In other words, once you get the proof of principle with a local delivery system, then you can start using those principles across the board. So that once the idea of local delivery from polymers was established and then approved by a regulatory authority, you could use it for many other situations. So now it's used in drug-eluting stents, as Aaron mentioned. That's changing the drug, but the same approach is used. And people are exploring that for many other things. So I think a lot of the things that are done on a scientific basis are done to try to create a whole new way of thinking, a whole new medical entity. But then when you actually pick the drugs, I think the problem is if you try to change 2 or 3 things at once, places like the FDA in the United States will not accept it. So you'd probably try to change one thing, which is the material or the approach, and that's generally what the companies have done, what the clinicians have done. I think as we go to the second part of your question, what will we see in the future? I think we'll see all kinds of things. I think we'll see, and we're starting to see this already in animals and in some human trials, you'll see hopefully targeted nanotherapy to take old drugs like anti-cancer drugs, but make them better because you'll get a high concentration right at the tumor rather than the rest of the body. And I also think sometime in the future, and again this will take time, we will see genetic medicines like siRNA and things like that can very specifically shut off genes. But there's a lot of work that has to be done also on delivery systems and on the science to get them to the right targets. So I think we will see all kinds of things, again, as we move over the next many decades.
Bien, yo creo que estamos acercándonos al final. Professor Ciechanover has, I will say it in English, has, I was going to tell all of these gentlemen to go, and ladies and gentlemen, to go to your talk to find out whether all illness have a cure, but you have revealed the secret. So we will be losing about 50 clients, but no, it's a joke, because I want to tell you that today, Ernst, Aaron and Bob will be talking in the Kursal, in the big cube. So even if you are not registered, you can go. It will be a space, but go early at 5 o'clock. You already know the answer to the question of Aaron, but there will be fascinating new ones that will arise, no doubt. And I would like to thank the three of them. They have told us that the man of Renaissance man, is not possible in medicine. Even Einstein was not in physics. He said that Thomas Young was the last man to know everything. But maybe the concept here has arisen of the Renaissance team, because knowledge is growing exponentially. So this interdisciplinary is more and more necessary, but at the same time more and more difficult. But that is what makes life and future interesting. And I would like to congratulate our three speakers for the inspiring and brilliant communication. Thank all of you for your assistance, and see you this afternoon at the Kursal. Thank you very much.